Okay, so we're going to be taking what we've learned now about seismic waves, and we're going to be working on locating the epicenter of an earthquake. And so I want to start with a story about you and I. And as I tell this story, you might find it a little far-fetched, but in my story, different characters are going to represent different seismic waves. Okay, so let's say that we were at school together and I challenged you to a race. Let's say I said to you, I've really been working out and I think I can beat you in a race. And you say, Mrs. Fickus, I really don't think so. I mean, I'm pretty fast, but we'll race anyway. So let's say we go down to the track, and you know that the start line is the finish line, also when you do one full lap. But anyway, let's say that I say to you that the 100-meter dash is my best race. And you say, okay. So let's say that the starting gun goes off, we take off and do a 100-meter dash, which is just 1/4 of the track. And I win. I beat you because I run at a steady, constantly faster pace than you do. Well, you get all upset and you say, Mrs. Fickus, maybe the 100 is not my race. Maybe I can beat you in a 200. So a 200 is half of a track. So the gun goes off. I still run at a constantly faster pace. You still run at a constantly slower pace. And so I beat you again. But this time, I beat you by more because I'm running constantly faster and you're always lagging behind. So this time, I'm waiting longer for you to cross the finish line. Then you say, I know what it is. My race is not the 100 or the 200. I would be good at the 400-meter dash, one whole lap. Well, I still run at a constantly faster pace than you do. You run at a constantly slower pace. And so what of course happens, now think it through, is that I still win the race. But this time I have more time to turn around and taunt you and say, na, 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 I won the race. Okay, now let's think it through. Ready? We were both representing seismic waves. I was constantly faster. So what wave was I representing? You were constantly slower. What wave were you representing? Okay, now let's apply this now to our background questions on our locating the epicenter activity. Okay, so you should have this idea for the first one. The energy travels in the form of seismic waves, and that happens in all directions, all directions. And there are two main types of seismic waves that we're concerned with here, primary and secondary seismic waves. Now, remember from our previous lesson, primary and secondary waves are not the scary ones. Those are the surface waves that head to the surface and do damage. Primary and secondary seismic waves actually help us to figure out the epicenter of the quake. Now, if you look at question 3 for me, you're going to put primary and secondary again. And so let's really make those speeds make sense. Primary waves can go 1.6 kilometers in a second. That's about 4 miles in a second. And it's easy to type that. But now let's think about what this means. That means that if there was an earthquake at our school, that the primary waves could be to the courthouse in downtown Newark in about 1 second. Now, the S waves are slower, so they don't travel quite as far in that same second. They only go at a rate of 4.1 kilometers per second, but that's still about 3 miles a second. They can go from here, from our school to the basket in just 1 second. So the point is, when we call secondary seismic waves slow, are they really slow? They're not super slow, but they are slower than the primary waves, just like you were slower in my story than I was. And so now number 4 is brand new for us and an important question. You might have heard me use this word in my story. What we say is that the secondary seismic waves always lag behind the primary waves. A difference in their arrival times is called the lag time. Now, number 5 there is a key concept. The shorter the lag time, that means the closer you are to the epicenter or the starting point. So if it's like the pre-waves get there and then the S quickly after, those waves didn't have far to travel, so the S waves couldn't get nearly as far behind. So that's the background questions. Now I want you to check out this. This looks kind of like a lie detector test, and it is not. This is a seismograph machine, and the thing inside of it is called a seismogram. Hang on, I think I have to sneeze. Oh, sorry about that. Okay, so the seismograph machine, the data that comes out is called a seismogram. And so do you notice there's a little needle here, and that records the seismic wave activity. It's very sensitive and can record them from very far away. So what we have today in our activity is we're going to use real seismogram records, and we are going to be figuring out the lag time and then using that lag time to calculate how far each city is from the epicenter. So you actually have this right here in your packet. And so, or I should say on your dock. And so what I want you to do with that is try your best next to figure out the lag time. Now you notice that the 0, I've put in a P here for you. So those are the primary waves. And then this first blip is when the secondary waves. Also notice that these count up by tens. So try that, and then in the next video, we'll see how you did.